We are given this definite integral of the function y equals x squared minus 4. We know that to be a parabola of perfect width, translated 4 units down. And we're asked to evaluate this definite integral from 0 to 3. Now, we know integrals provide us with area under the curve. It's important to recognize that the term under the curve is really false advertising. It's really the area between the curve and the x-axis. So here in this section from 2 to 3, it is indeed area under the curve, but you can see here, this is area that is technically above the curve. When we take our antiderivative and we plug in our beginning and end points, we get this value of -3. So clearly there are more portions of this total area under the x-axis where it's considered negative than the area above the x-axis. Now, I'm pointing this out because we have a definite integral with a negative value. A definite integral could be positive, 0, or as in this case, negative. Now, compare and contrast that to this situation where we are asked to find the area between the two curves, x squared minus 4 and y equals 0, otherwise known as the x-axis. So folks, when you have area between the curves, that is a physical space, and this is always going to be positive. And the reason is the calculation of the area of this total physical space is structured so that the function with the larger y value is in front, and the function with the lower y value is behind the minus sign. So you can see here in section 1, as we move from 0 to 2, the function y equals 0 is first, and then we subtract from that the lower function. And then when we move to this zone, integral from 2 to 3, we see that the reverse happens. Now we have the parabola above the x-axis, so therefore it is listed first in the formula. And when you compute the area of when you do the definite integrals of both of these sections, you find that from 0 to 2, you get 16 over 3, a positive value. That's because of the way this is structured. And when you do part 2, from 2 to 3, you get 7 over 3 for a total area of 23 over 3. And up here in the corner was our result from the definite integral. So it's important to understand when you're taking area between curves, you're always going to get a positive answer. When you're taking a definite integral, which is thought to provide area under the curve, remember it's the area between the curve and the x-axis. That's when you're using vertical rectangles anyway. And with this definite integral, it's a net. So you may get a 0, you may get a positive, or you might get a negative value. So to review, if we have this function here, and we're asked to take the definite integral, say from x equals -10 to x equals +10, you could see we're going to have some negative signed areas, positive, negative. This whole definite integral would definitely be negative. However, if we're asked to find the area between the two curves, y equals 0, which is of course the x-axis, and this function, whatever it is, this section's going to be positive because the integral is going to be set up with the top function minus the lower function. This is going to be positive. Again, it's going to be the top function minus the lower. And this is going to be positive, top minus the lower. And if we're integrating with respect to the y-axis, it's going to be left minus right. So if we're integrating here, it's going to be the right side minus the left. It's the higher x value minus the lower x value. I typed this into Google And I think this is an excellent explanation of what we've been talking about the last few minutes, if you want to take a screenshot of this. But basically, it says, here's the key point. The area between two curves is always positive, while the definite integral of a function can be positive, negative, or zero, depending on the function's behavior and the integration interval. When you're finding area between the curves, you are calculating the space between them. It's a physical space, a physical quantity. The integral is set up so that the larger function is going to come first, and you're going to subtract the smaller one to yield a positive result. When you're doing a definite integral, it calculates the signed area between the function and the x-axis. So you're going to get positive, negative, or zero with the definite integral. On the left, we have a typical definite integral where we are using dx as the width and f of x as the height, and we are summing these vertical rectangles. When you're in this scenario, we have the expression y equals f of x. This is what we're used to seeing. We solve for y, and when we do our integral, you see that the variables within the integral, namely the x, matches the dx. In this video, we're going to talk about how to integrate with horizontal rectangles that involve a width of dy and a length, if you will, of f of y. So in these particular problems, we're going to have x equal to f of y. We're going to solve for x. Here we solve for y. Here we solve for x. We're going to have all y's in our integral, and we're going to match that with the dy. In our first example, we will be integrating using horizontal rectangles. So as promised, we're going to have dy involved. That's going to be the width of our rectangle, and we're going to have f of y as the length. So you could see that our two curves are solved for y. We have f of y and we have g of y. So we are going to set up an integral with y values going from a low of -2 to a high of 1. And we're going to have the y variables in here times dy. We're going to do the right function first, and we're going to subtract the left function. So the right function is going to be 3 minus y squared. And then we're going to subtract the left function, which is y plus 1. Again, both solved for x in terms of y. Oops, that should be a dy. And this has to match the variables within the integral. Okay, we're going to take the antiderivative of this, and we're going to end up with, when we simplify this, we're going to have negative y squared minus y plus 2 dy. We're going to take the antiderivative here back in black, and we're going to have negative y cubed over 3 minus y squared over 2 plus 2y, and we're going to evaluate that from -2 to positive 1. Okay, when we plug in the numbers, we're going to get -1/3 minus 1/2 plus 2. That's when you plug in 1, and from that we're going to subtract plugging in -2. And when we plug in -2, we're going to have 8/3 minus 2 minus 4. Folks, when you do all your math and you simplify these fractions, you should get a value of 9/2. And that is our area, despite the fact that we have portions of this area underneath the x-axis that is irrelevant. This is the area between two curves, and we will get a positive answer because of the fact that we set it up the right minus the left. We are going to do that same problem, but we're going to use vertical rectangles. When you use vertical rectangles, the dx, the width, is dx. The width is going to be dx, I should say. So our integrals are going to be involving dx. If our intervals involve dx, that means we have to have x in the integrand. To have x in the integrand, we have to solve for y. So let's go ahead and solve both of these functions for y and see where that takes us. So here we're going to throw the y squared on the opposite side, and we're going to throw the x on the opposite side. So we're going to get this. And then we're going to take the square root of both sides. When you take the square root, when you're solving for a variable, you have to add plus and minus. Over here, it's a little bit more straightforward. We're just going to get y equals x minus 1. Okay, now that we have our functions in terms of x, this is y equals f of x, now we can do our integration with respect to, with using dx in the integrand. As we get set to integrate with vertical rectangles, we're going to be using dx throughout. Notice, folks, that this is a crucial point here, where x equals 2. Now you have the y equals square root of 3 minus x function and the negative version of that. So that's different than when we had the horizontal rectangles, when this curved function was always to the right of the linear function. Now, for the first part of this integration, we're going to have the linear function above the curved function, but then once you move past x equals 2, you have positive curved function over the negative curved function. So let's analyze this curved function before we get into the math. So we solved for y. Why are we solving for y? Because we're dealing with dx. If you are taking integrals with dx, which is what we're doing, how do we know that? Because we have vertical rectangles, and vertical rectangles have dx as a width. If you're taking integrals with the dx, you have to have x's here. If you have x's there, you have to solve for y. And in this case, when we solve for y, we get two different functions, a positive and a negative version. So let's think about how to graph both the positive and negative version of the square root of negative x plus 3. First of all, we set the integrand equal to 0. We solve for x. We get x equals 3. We plug that in, and when we do that, we get the y value. So we know that this vertex right there is going to be 3, 0. Now, the question is, what do each of these graphs do from the vertex? Well, if we look at this first part, you have a positive outside of the radicand, positive outside of the radical, and a negative inside the radical. That means this portion of the graph is going to go where x is negative and y is positive. Where is that? None other than the second quadrant. So you could see here, when you have a negative in front of the x and a positive outside of the radical, this graph is going to head towards the second quadrant. Down here, when we have a negative in front of the radical and a negative with the x, this is going to end up, its end behavior is going to head towards where x is negative and where y is negative. Look, x is negative and y is negative. That is the fourth quadrant. So here are our two functions. We have that and we have that, both emanating from this vertex. Let's now proceed with part 1 of the integral. So part 1 is going to involve this section here. So we're going to go from x equals -1 to x equals 2. We're going to have the linear function on top of the curved function. Here's our linear function right here. On top, we're going to subtract our curved function. Our curved function down here is negative square root of 3 minus x. That, if you switch the x and the 3, that's negative x plus 3 to the 1/2 power. There's your negative. When you apply negative times negative, you're left with this. Okay, so here in the first part, we're just going to take the antiderivative of x minus 1. That's going to be x squared over 2 minus x. There should be a 2 under here. I apologize. Let me change that. X squared over 2 minus x right here. Okay, now with respect to this part, we're going to use u substitution. We're going to let u equal negative x plus 3. du is going to be negative dx. dx is negative du. We're going to pull the negative out front. There's your du. The negative du was your dx. Technically, there should have been a dx here. I apologize. Okay, when you take the antiderivative of u to the 1/2, we're going to add 2 over 2 to get 3/2. We're going to divide by the new and improved exponent, which is the same as multiplying by the reciprocal. And when we do that, we're going to get negative 2/3 times negative x plus 3 to the 3/2. That is your antiderivative. So here, we're going to take x squared minus x. That's the first part. Here's your second part. And we're going to plug in first the 2, then subtract that from the negative 1. And folks, when you do that, the math will compute to 19 over 6 for that first portion of the integral. That green is hard to see. Let's go ahead and redo that in black. So this area right here is going to be 19 over 6. Now that we have the first part of the problem solved, we have 19 over 6 is the area from x equals negative 1 to x equals 2. Now we're going to compute the area here, which only involves the curved function. On top, we're going to have the positive version of the square root of 3 minus x. On the bottom, we're going to have the negative version, and we're going to do top minus bottom. When you add these up, you're going to get the 2 out front. We're going to let u equal 3 minus x. du is negative dx. dx is going to equal negative du. We're going to pull that negative out here. See that black negative with the du? That's your negative du. That used to be dx. We're going to take our antiderivative. We're going to add 2 over 2 to the exponent and get 3 over 2. We're going to divide by the new and improved exponent of 3 over 2, which is the same as multiplying by its reciprocal. That gives us negative 4/3. Let's go ahead and back substitute the u to the 3/2. When we first plug in 3, and then we subtract plugging in 2, we get 4/3. So 4/3 is going to represent the area of this portion of our problem. If we come over here to the right, we remind ourselves that when we used horizontal rectangles, which were easier, our final was 9 over 2 for the area. Here, we're going to add 19 over 6 plus 4 over 3. That is 19 over 6 plus 8 over 6, 27 over 6. And we end up with 3/2, which matches the value that we got when we used horizontal rectangles.